Hey folks, this is Sanjeev from vNext Labs, and today I'm going to be showcasing to you how to use the color sensor with the Lego Spike Prime. This is the Lego Spike Prime. If you do not know, this is the new robot that Lego has actually brought in. This robot is actually evolution of probably EV3. At this point of time, we do not know whether they are gonna replace EV3 with this one. But that being said, there are a lot of new elements, and the programming model has switched from the block, or I should say, the EV3 Mindstorms based programming, which was a lot more visual to Scratch, which in my mind is pretty great because we have seen students take on to Scratch a lot better than the previous model. Anyway, so here this thing just came out in January, and there aren't many examples and so on. So we thought that we would create a really good tutorial for you to figure out how to use the color sensor to follow a line. On the way, we are going to show you a few tips and tricks that we actually saw that threw us for a curve. Without any further ado, let's look at the robot and the color sensing along with it. So on the screen, you can see we have this uses actually the new programming model, which is the Spike Prime programming model. So it is event based, and so one of the events, the first event that you see over here is when the program starts, right? One of the things that you have to do is you have to set the movement motors. On the Spike Prime, all the ports are exactly the same: A, B, C, D, E, F. There are 6 ports, and all of them can use motors or sensors. And you will have to tell the Spike Prime which motors are your driving motors, or which ports contain your driving motors rather. So here we are saying we just built the chassis that that Lego provided. We didn't think about creating a new one. We will create a new one. It will be part of our book. That's coming up on winningrobotics.com, but for now we just use the one that's Lego provided, A plus E. We said those are the ports that are hosting the motors that are driving the robot. And then below that you can see we actually created 2 separate blocks. I'm going to move this one over here. One for Bangbang color sensing, or I should say not color sensing. I should just edit this one and say Bangbang color, Bangbang line following. Save it because it truly is line following. So if you're not familiar with line following essentially is not really line following. It essentially is edge following. So you can see on the screen on the on here, when you have a line, essentially, like when you have a line, your robot can sense where the line ends and a different color starts. For example, let's say if you have a black line, then as you can see on our screen on the bottom left corner, there's a kind of a square with the rounded corners that I created on a white board with the black electrical tape. So when you are looking at a line, you can only follow the edge of the line. You cannot follow the line per se. An example that I have given to kids in the past is, let's say you are Dorothy and you're trying to follow the yellow brick road to the Wizard of Oz, right? And let's say if the road is let's say a mile wide, right, and you're sitting right in the middle of it, when you look at it, can you really follow the road? The answer is no, you cannot, because you don't know which way is forward, which way is backward, which way is left, which way is right. You just have this expanse of same color all over the place, right? So you can't. But if you are on the edge of the road, then on one side of the road you see that it's dirt or trees or whatever, and on the other side you have the yellow brick road, and so you know, oh wow, this is an edge and I can follow that. That's exactly the principle that the robot actually follows. So what the robot does is, it essentially, when it sees the color that we want, for example, let's say we're trying to follow the left edge or the right edge of a black line, right? So the robot color sensor will sit on top of the, let's say this is the line, the color sensor is actually looking at the line, and the color sensor is partially on the line and partially off the line. So some of the color sensor is going to see black and some of it is going to see white. And then it can figure out, oh, I am on a line and I can continue following this difference in shades, which is white and black, and continue moving straight, and that's how the line following works. Everybody calls it line following, but in reality it is edge following. And with that, it should give you food for thought that you can follow the left edge of a line and you can follow the right edge of the line, and the programs for the two are going to be slightly different. The left is not going to be exactly the same. The conditions are going to be inverted. Anyway, so in our program, the first thing that we did over here was we set the on the event when program starts, we set the movement motors to A plus E. And then we wrote 2 functions. These are functions, or my blocks. They used to be called in EV3 Mindstorms, and good for us that Lego has decided to keep the same name in the new Spike Prime studio. So these blocks can be created by going over here. You can go over here and then you can say make a block, and then it'll ask you for a name and inputs and outputs and so on. In our case, we didn't want any input or output because we are just showcasing a simple block. So one of the simplest way of following a line is that one of the simplest way of following a line for a robot is, this is your color sensor. Let's say this is what your color sensor is seeing, and this is the line over here, or rather I should say this way, this other way, right? You have, this is the color sensor, it is seeing the line, some portion of it, and it's half and half. So it sees black, it should move to white. And it's not simply turning, it actually, there are two wheels to the robot, right? So let me show with the help of the robot. So here's the robot, right? And what it means is, let's say this is the color sensor over here, and the color sensor sees a little bit of black, right? Which means, and the white is on this side, and you're following the left edge of the line. If it sees black, it should turn a little bit to the right. And when I say turn, this wheel actually is held, and this moves a little bit faster. So the robot actually moves a little bit forward while at the same time turning. And then the color sensor, of course, will move from the black to the white. And as soon as that happens here, black to the white, you immediately hold this wheel, the right wheel now, and turn the other way. So it kind of moves like, this. It moves like this. It moves in a zigzag fashion, almost like a person who is inebriated or drunk and cannot find their way. They are like, going left and right and left and right. It's called Bangbang because it when you see the robot motion, I will show you the robot motion in a little while when I go over the execution of the actual program. It moves very jerkily, like goes left, goes right, goes left, goes right. And even though it is a fine program to teach, especially younger kids, it is much I would say it is very inaccurate, because you don't know, when you stop the robot, you don't know whether the robot is going to be facing the correct way. It may be facing slightly this way or this way. So if you have something that you want to do over here, you are not sure if the robot is actually facing that way, and there is really not, you will have to go and figure out another sensor or some other means of again figuring out your position. So that doesn't make too much sense to us. Like, even though Bangbang is taught and Bangbang is something that students are very easily understanding, that is something we don't necessarily advocate for use in the competition. So anyway, let's take a look at the Bangbang line follower. So if you look at the Bangbang line follower, it is very straightforward. You have an infinite loop here, we say forever. Of course, in a actual competition setting, you will have a way to terminate the loop. We are leaving that as an exercise to you. What you do is, one of the things is, you have to remember the color sensor in the Spike Prime, and for that matter in EV3, had two modes: the color sensing mode and the reflected light intensity mode. In the reflected light intensity mode, the color sensor throws some light on the surface and gets back some of the lights and measures it. So the light that it threw, it assumes that's of value 100, and what it gets back, it grades it between 0 and 100. So black surfaces absorb a bunch of light, so they will reflect less light, and white surfaces absorb very little light, reflect most of it, so you will get pretty much most of the light. The reflected light is given to you in a range of 1 to 100. And so you are saying, assuming like, what we really want the sensor to be is ideally 50% on black and 50% on white, so it's moving perfectly following the line, right? So we say, hey, our color sensor is on port B. So we are saying if the color sensor on port B has a reflected light less than 50% of what it threw out, then move one of the motors, which is the left motor, this way, like a little bit more with more power, and hold the right motor. So what will happen is, this is actually following the right edge of a line. So this will, if you see less than 50%, which means you are more on black, then you need to get on the white, so you turn this way. And if you are more on the white, then you turn the other way, which is what this other one does. Like if you have more than 50% light coming back, which means you are more to the right of the black line, then you go this way. So this way and this way, and that's all it does, right? I mean, move back and forth, and it works very beautifully. In general, this is a very robust algorithm. We have seen it fail very rarely, but that being said, it is of limited use because at the end of the competition, or sorry, at the end of the run, you're not sure which way the robot is oriented. A better way to do this is the proportional line following algorithm, and this is hard for kids to understand, sometimes even for adults. But proportional is a very straightforward process if you look at it. For example, if you are looking at let's take the context of a bicycle, right? Most of you know how to ride a bicycle or a bike for the matter. So when you're riding a bike, when you get onto the bike, right, you have almost no motion, so you're just pushing it and you're getting on it, and your bike swerves left and right quite a bit. As you start riding, the bike becomes very, very smooth, right? You're not going left and right unless you really want to. If you are just riding in a straight line, your bike will run very, very smoothly. Do understand that your hands are making corrections, a little bit to the left, little to the right, little bit to the left, little bit to the right, and so you're correcting. If you suddenly see something very, very weird, for example, let's say you see a sharp turn, you do a very strong correction, you will not do a gentle correction. So what I guess I'm trying to do say is, when you start and you're not exactly where you're going, for example, when you start biking, when you start riding the bike, you are doing very large motions to get to the right place. But as you get to a state where things are working as they should, you don't need to make very large corrections, you do small corrections. So in that sum, you make corrections in proportion to how much out of the ideal state you are. That's all proportionality really means. There is a much more complicated version of this thing called PID, which is called proportional integral and derivative, which is a algorithm that is used in control systems quite often, nuclear plants and so on and such. You don't need to understand the whole of PID. For our robots, the proportional is sufficient, and proportional, all that it means is apply a correction of error only as much as error you have. So like in the bike, in the beginning, you are very far from the ideal state, you are not riding straight, so you do a lot of left and right with your handle, and when you get to perfect riding state, you do very little corrections, right? So the way this is described essentially is midpoint over here, this variable here is 50, and what it means is this is what the color sensor should be seeing. Ideally, when the color sensor is fully on black, it will see 0. When it is fully on white, it should see 100% of the light reflected. So midpoint is right in the middle. That's what we would like to have. That's the ideal, so we call it the midpoint. And then we give a default motor power. For example, like we want in whichever case we want our motors to be running at about 30% of the power. So we just put a power at 30%. I picked 30% because for the Lego Spike Prime, the robot that I have built, it uses the larger wheels, and giving a very large amount of power to this one causes the robot to move very quickly without giving the sensor sufficient time to read the value and for algorithm to be able to process the input. So it just goes haywire. So if you're using smaller wheels, you may actually end up using larger values for the default motor power. And finally, there is this thing called KP, which is 0.4 we have put. And if you don't get it, it's not a problem. But what KP does is essentially, when you are applying the error correction, you are doing a lot of left and right on your bike. You may sometimes want to scale it down a little bit to put it under range. For example, you cannot jerk it so much that your bike falls, right? So you may want to taper your motions, you may want to correct your motions, you may want to say, hey, somehow I'm gonna block the handle of my bike so it cannot go past a certain tilt. Like there's no point in the front bicycle wheel actually tilting more than about 90 degrees, right? I mean, your bike cannot go anymore, so you can block it somewhere. So in some ways, the KP is a factor. It's a constant factor that forces your algorithm to produce values that are within range, and also it is used for the smoothness of the algorithm, as in how smooth your algorithm performs. You can read a lot more about it in our book. The book is on robotics.com. The Spike Prime book is coming, and the EV3 book is already there. But that is sufficient for most people to understand. Trying to understand it a lot more is not super helpful. Anyway, so once we have the KP, the midpoint, and the default motor power, all you really need to do is say midpoint, from the midpoint subtract the reflected white light value, which is how much I am actually seeing, how much is my color sensor actually seeing. So ideal is 50% of the light. If you see exactly 50% of the light, this is going to be 0, right? Midpoint minus reflected light is going to be 0, and your KP multiplied with will get multiplied to 0. The answer will be 0. And so we will move the robot by putting the default motor power in the left and default motor power in the right. And if the error is 0, which is to say, like, your color sensor is seeing exactly 50% of the light, then your robot will move perfectly straight, which is what we want. Except if the robot has even a little bit of jaggedness, or if your path is moving a tiny bit, then the color sensor will actually move slightly to the left or slightly to the right. The motion may be very, very little, but the color sensor is high fidelity and it will pick it up. So if that happens, then we measure, by doing this subtraction, we measure how much deviation has happened, how much have we moved away from the actual ideal state, which is like, the color sensor should be ideally 50% on the line and 50% off the line. And then we multiply it by the KP, the number. This number is experimentally determined, as in if 0.4 doesn't work for you, try 0.3, try 0.5. You have to keep this number less than 1. for mathematical purposes. You can read more about this in our book, but in general, between 1 and 0 is the value that you would put for the CRP, and you can experimentally verify. Just keep trying in 0.1 increments until something works for you. And then so you get the deviation from the ideal state that you should be. You multiply Kp to it, and then you say, hey, this is my default motor power, and if I am away from the ideal state, let's say if I am if I am too much on the black line, then I need to go to the right, because I'm following the right edge of the line. So I need to move a little bit to the right, and I'm too much on the line. So what I do is this motor gets a little bit more power. That's what we do over here. We say default motor power plus the robot turn amount. Whatever we calculated, the proportional amount, we are going to increase this turning, and by the same factor we are going to decrease this one. So the robot will turn slightly like this, and as soon as it goes off black into the white, immediately the light reflected will be more, so it will go left and right. By doing this proportional instead of just the two-state algorithm over here, this makes our algorithm runs a lot more smoother. So without any further ado, now let's go and experiment with the robot. And I have a quick tip and a showcase on the robot design to make sure this PID algorithm works well for you. So let's take a look. Okay, so here we have our spike prime robot on the line, and it is on the right edge of the line. And let's try and put the Bangbang line follower over here, and let's run it and see what happens. As you can see, it is jerking about quite a bit left and right, left and right, left and right, left and right, and it'll continue and it'll follow through the entire circle. But let's stop it here. This is not the algorithm that we would really want you to use. The other one that we want you to use is the proportional, right? So you can see even on the straight. Let me run it one more time. This is the straight segment of the square, and it is still doing quite a bit. And now it's going towards the corner, and even there it will do this zigzag, 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 and that is that works, but not necessarily the best place that we want it to be, right? So now if we take the Bangbang line following and move it over here, and instead put the proportional line following to the right edge, right? And let's try this one. And you can see it zigzags a lot less, it moves a lot more smoother, but you can still see it actually zigzags at the corners of the square. It actually zigzags, and then when it sees a straight line, it smoothens out a lot. And there is a reason for why this is happening, and I'm going to explain to you. This is not a issue with the programming. This is an issue with the robot design. Quite a few people actually try to use the let me stop this, it's making much of noise. So quite a few people try to use a PID, and they are like, oh, my PID is not working. I have the completely perfect algorithm. What is happening? And let me explain. Here is the reason why it doesn't work. So here you can see that the color sensor, when the spike prime robot was designed, or this is the actual design that is given by Lego. First of all, the color sensor is mounted too low. Even Lego documentation says that the color sensor should be mounted 1.6 centimeter, ideally from the bottom of the surface that's trying to measure, but they have measured it, put it around like less than a centimeter, so it doesn't work very well. So I had to actually move it a little bit up. But even here it doesn't work very well. It is mounted at the perfect height, but still the motion of the algorithm doesn't work very well. And the reason for that is the driving motors are over here. So if you can see, the color sensor is over here and the wheels are over here, right? This is the difference. This is the color sensor. I don't know if you can see it very well there, and here's the wheel. So there's a lot of difference between the color sensor and the wheel. And what that does is you have to actually imagine what happens. Let's say if you are wearing very long shoes, what happens? Whenever you're walking, the front of your shoes keep hitting the front surface, some surface, and you keep on falling all day long, because you have an approximation where your foot is, and you're moving your foot according to how small or how large your foot is. But you have extremely large shoes, and you're not used to the very large distance. You're not accommodating the extra distance, and your feet keep hitting the walls. That's the exact same thing. The robot motion, which is trying to correct the cache onto the color line, that process actually happens at the wheels. The motion of the wheels is that tries to keep the robot on track, right? Except that the measurement of the color, how far we are away from the line, that happens at the color sensor. So the more the distance that you have, the more it is like the really large shoe. Like the measurement is happening somewhere else, but the correction is happening somewhere else, which means the robot is correcting for something that it will hit in future, because of which inaccuracies pile in, and because of which your robot keeps on doing this thing left and right, left and right. This is not an ideal way to do the robot. What ideally we should do is we should move this sensor much closer to this to the motor, and let me try and do that and showcase how the exact same algorithm without changing anything, the exact same program, works much better when you have this. So let's try it out. Okay, so the color sensor is now mounted over here. This is the second color sensor that Lego put right up here. You can see it, and this is where I moved it. It is right in front of the motor. So now let's see how the behavior of this one is. Okay, so now let's see if we run this robot, what happens. You can see the motion is a lot more smoothed out. I haven't completely perfected it. I didn't have sufficient time to completely perfect it, but even at the edges, even at the corners, it moves so much smoother. And I did not change anything except the position of the sensor. You have to move the sensor closer to the motors so that it moves smoother. And you have to remember, you cannot move it behind the motor, because then the motors take an action that has already happened in the past. Like the color sensor is seeing something that the motors has already finished, right? So you have to keep it in front, but really just a little bit in the front. So that is what it is, folks. I mean, this program is available. We will make it available for download at winningrobotics.com. You can download it from there. Although, given that it is just a few lines, you may just make use of it right here. That's all for this time around. Thank you so much, and see you next time. Please subscribe to our channel. We would love to connect with you, and thank you for watching.